This video is going to cover the definitions of physical laws and theories, some key concepts, and some key philosophical concepts in the way that people talk about physics and do physics. The first of these I want to really highly emphasize is the difference between physical laws and theories. In the world outside of academia, the meaning of laws and theories has become very much conflated and very confused, and it has created some serious problems in education and in the way that people deal with science as a whole. We need to be very careful about this, both internally when we're working for ourselves and also externally as we deal with the general public. So let's begin by talking about basic definitions of these. A physical law, or a scientific law, is based on empirical data. They expose relationships, but they do not explain underlying reasons. This is a key difference. There is no attempt to propose a mechanism for a law. It is simply based on data. The physical theories, or scientific theories, are mechanistic explanation of events. Now, this does not mean that theories are any less required to correspond to physical reality, to actual measurements. They are, but they are mechanistic explanations of events. They can be derived from first assumptions or from first principles, and frequently they will predict the form of some law, either previously observed or later found to fit it within the context. There is, however, an important distinction. This is not a hierarchy. Theories are not subsets of laws. Laws are not subsets of theories. Frequently, one will use a set of laws in developing a theory because both of them are required to correspond to the actual observed reality. But they are different entities. They do not transform into each other. So you can have data supporting a law, you can have data supporting a theory. You can have a well-accepted law, you can have a well-accepted theory, you can have a rejected law, you can have a law that is not correct, you can have a theory that is not correct. There is no hierarchical sense. There is no implication of correctness or incorrectness for either of these concepts. And that is important because you'll notice that when lay people in particular tend to use these terms, they tend to use them as if laws are true, which is not correct, and as if theories are unproven differently than a law, and that is also not true. Theories can be proven to be incorrect. Laws can be proven to be incorrect. That still does not make the law anything other than a law, and it does not make a theory anything other than a theory. They are different entities. They don't transform. Neither of them is suggestive of correctness. No amount of evidence will ever transform any theory into a law. They do very different things. Laws describe, theories explain. Other key concepts that we're going to be discussing in this unit this week are the assumptions for the classical theory of motion, some key motion terms, and Newton's laws of motion, which are roughly the law of inertia, resistance to change in motion, the law of mass, the law of acceleration, the way that motion changes, and the interactions, or forces, which cause the motion to change. So first we're going to take a step back and look at classical versus classics. So Greek theory versus Galilean Newtonian theory. In ancient times, there was a view of motion that was very highly developed, and one of its characteristics was that it required a source of animation to keep things in motion. And this was based on the very real observation that in everyday life, objects always stop moving when left to their own devices. If you have a box and you're pushing it across the floor, when you stop pushing it, it will stop. And even in modern times, this is generally how people think about the world. It's a very what we call Aristotelian view. And it's very difficult to overcome this because it is so common. And it has to do with the question that is asked. Classical physics, led by Galileo, turns this question on its head. And instead of looking for reasons for objects to keep in motion, classical physics looks for causes of the change in the motion of objects. And Newton's first law, as stated by Galileo, an object in motion or at rest will remain in motion or at rest unless acted upon by an outside force that would be outside the object. It gives much better results, and it doesn't require intervention for things like planets to keep moving. One of the problems that Aristotelian mechanics has is how is it that the planets don't stop moving as they go across the sky? And this led to proposals of ideas like giant chariots hauling planets across the sky. But it turns out that if the planet will move unless something is acting on it to cause it to stop or change its motion, then you don't need the giant chariot pulling the sun across the sky. The sun will go across the sky, or appear to, because of the tendency to remain in motion. So it's a very different view. It's based on a very different question. So the Aristotelian view simply starts from the wrong question. The question is not, why do objects keep moving? The question is, why do objects stop? Highlighting again the importance of asking the correct question. And lastly, a few assumptions of classical mechanics which turn out not to be true, but that turns out not to matter for most purposes. So the first one, objects occupy one and only one point in space, time, at a time. And while this seems to be obviously true, it's a concept called locality, it turns out that modern physics, modern in the early 20th century sense at least, has locality break down to at least some extent or another. But classically, we assume this is true. We assume space is continuous, meaning there is no non-existence between points in neighboring space, and isotropic, meaning that space is the same in all directions. And that seems to hold, certainly in the world that we live in, at the size that we are, those two things seem to be safe. Although it turns out that space is probably not continuous and may not be isotropic, but probably is. And then the other assumption that all observers measure the same displacement between 2 points in space turns out to be not true. It's approximately true for things that are not moving very fast, and therefore it works. It's a very effective assumption, but it turns out not to be perfectly true. Similarly, we assume that time is continuous and isotropic, and that all observers measure the same durations. This also turns out to be not quite perfectly true, although it's true enough for objects that are our size and live at our time scale. The next video will deal more explicitly with Newton's laws of motion.